All right, in this section 4.8, we're going to give you one last way of solving a systems of equations, and this time it's going to be using inverse matrices. And we're only going to do this for a 2 by 2 system, okay? So let's get right into the concept of a matrix equation, okay? If you have your 2 by 2 system written in standard form, both equations in standard form, you can transfer that into a matrix equation very, very quickly, okay? So the matrix equation is going to have three matrices to it, a coefficient matrix, a variable matrix, and a constant matrix, okay? The coefficient matrix is exactly what it sounds like. It would have the coefficients of the variables from the two equations in the same order that you see them, showing up in the two equations, okay? So you're going to take that coefficient matrix, you're going to multiply it by a variable matrix, which is simply just going to be x and y. So whichever variable is written first in your two equations, in this case it's x, that's going to make up the first row, first column element, and then your second variable would make up the second row, first column element. And then you're going to set that equal to your constant matrix, which is 9 and 8. Okay. And if you actually perform the multiplication between these two matrices, you're going to notice that it's just going to take you to the matrix 2x plus 3y for a first row, first column element, and then negative x minus 4y for a first or second row, first column element. So you'd have a 2 by 1 equaling another 2 by 1. Okay, so this is consistent with matrix multiplication in that it's going to result in the same system that you originally were working with. Okay, so take a moment, go to practice one, and I want to just make sure that you can develop the matrix equation yourself, okay, before we move forward. Okay, pause the video, try that on your own. All right, now that you know how to set up the matrix equation, let's talk about how we can use inverse matrices in order to solve this system, okay? So I notice back here, I assigned the letters of A, X, and B to my various matrices. So A is my coefficient matrix, X is my variable matrix, and B is my constant matrix, okay? So essentially I have the equation A times X equals B, and what I want to do is try to solve it for X, the variable matrix, okay? Now, one way to get X alone would be to divide both sides by A, right? Well, we don't have a concept of division with matrices, okay? So instead what we'll do to isolate X is we will multiply both sides of the equation by the inverse of the coefficient matrix A, all right? So when I do that, the inverse of A multiplied by itself will result in the identity matrix. And we know that the identity matrix multiplied by the variable matrix is simply just going to give you the variable matrix, right? So ultimately, in order to solve the matrix equation, I only need to take my constant matrix, which is matrix B, and multiply it by the inverse of the um, coefficient matrix. Okay, so let's put this into action with this system here. All right, let's first just come up with the matrix equation. Coefficient matrix would be 5 and 4, 3 and 7. You're multiplying that by your variable matrix, x and y, equaling 13, negative 8, which is your constant matrix. Okay, so again, this is like matrix A, this is matrix X, and this is matrix B from, the example above, okay? So now we're going to find the inverse of matrix A, okay? Which means we need the determinant of that matrix. That's going to be 5 times 7, which is 35, subtracted by 3 times 4, which is 12. That's going to give us 23. And the inverse of matrix A would be 1 over that determinant of 23 multiplied by the following matrix: 7, -3, -4, and 5. Okay? And I'm actually not going to multiply through by the scalar. I'm going to keep that out in front and save it for the very, very end. Okay? All right, so now I'm just going to show a tremendous amount of work, kind of as a bit overkill here to make sure we all understand the process, okay? So essentially what we saw up above is in this line, we saw that we need to be multiplying both sides of the equation by the inverse of that coefficient matrix, okay? So I'm gonna put that one in red now. So here's your inverse. Okay. And that is simply multiplying matrix A on the left side of the equation. And then on the right side of the equation, right, whatever we do to one side, we got to do to the other. So taking that same inverse for matrix A, and it is multiplying the constant matrix. All right. Now, provided I have found the inverse correctly, I know that the inverse of matrix A multiplied by matrix A is going to result in the identity matrix. Right? These two will come together to create that identity matrix. Okay. And that'll just leave me with the variable matrix. And then that's going to equal, I'm going to keep the scalar of 1 over 23 out in front, and I'm going to actually multiply these two together. Okay, so that's a 2 by 2 times a 2 by 1. That's going to result in a 2 by 1. Okay, so if I take the first row, first column elements, that's going to lead me to 115. And then second row from the inverse of A and the first column elements from B, that's going to lead me to -92. Okay. All right, and then we're almost done here. So the identity matrix multiplied by the variable matrix is going to give you simply the variable matrix. And then I'll multiply through by the scalar here. So 1 over 23 times 115, that's going to give you 5. 1 over 23 times -92 will give you -4. So in the end, you have two matrices equal to each other. Their corresponding elements are equal. That means x equals 5, y equals -4. So my solution to this system is the point 5, -4. Okay. Now, again, I think I've gone, kind of overkill here in this first example, just trying to show all the work to you. Understand, really, you don't need to show this much work. You can get away with just doing the following, provided you conceptually understand, how multiplying both sides of the inverse shakes out. So basically, whatever you see circled in purple here, this is what you would be, wanting to show for your work to this particular system, okay? All right, let's move to example 3, and something special happens on this one, okay? solve it using a matrix equation. So I'm just going to set it up right away. 10, 6, 5, 3 is my coefficient matrix. And then my variables, of course, x, y. My constant is 15, negative 6. Okay, so let's label A, X, and B as these different matrices. And if we're going to solve it using inverse matrices, we need the determinant of matrix A, first and foremost, which is going to be 30 subtracted by 30. That gives me 0. And that's a problem. That means the inverse does not exist. All right, so this is where the method of an inverse matrix fails us in solving the system. We'd have to go and use a different method, a different approach. And you just go back to one of your algebraic methods like substitution or elimination. What I'm noticing is that both of these equations can be reduced. This can be 2x plus y equals 3 if I divide all those by 5. And then the second equation is 2x plus y equals negative 2. And then I'll use subtraction to eliminate. Both variables eliminate, leaving the left side to be 0, and then the right side's 5. And of course, 0 does not equal 5. So I know that this system has no solution to it. Okay, so that's kind of one of the bad things about this particular method, is that it doesn't allow us to come up with an answer of infinite solutions or no solutions directly. We'd have to, refer back to one of our other methods to come up with that conclusion. Okay.